Michael Dahlberg. He's an avid beekeeper, and he's going to be talking to you today about detecting honeybee swarms using OpenCV, Pandas, AI, and PyTorch. So give him a warm welcome.
Hi, my name is Mike, and I'm a beekeeper. And no, you did not just wander into a strange beekeeper 12-step program. Who am I? I'm a Linux systems administrator. In addition to being a beekeeper, I've been fighting with Linux servers for 25 years, the past 6 at Penn State University, and a begrudging Perl programmer for about that same length of time. More recently, I've found inner peace as a happy Python programmer for 3 years. And for the past 11 years, I've been a beekeeper with a personality as unpredictable as my bees, somewhere between Zen monk and why are they all dying on me? This is a common sight in April throughout the Northeast United States. To a hive of honeybees coming out of winter, this is nirvana. The first sources of nutrition to emerge in the spring shown here are dandelions, followed closely by pears, apples, and redbud trees. With the rapid increase in resources, nectar and pollen, the size of the hive will rapidly increase over the next several months to approximately 65,000 bees. Within the hive, there are 3 castes of bees: workers, drones, and queen. All worker bees and the queen are female, all drones are male. All reproductive activity in the hive is done by the queen. All other tasks in the hive are delegated to the workers. This means that if conditions are right and there are the resources of pollen and nectar, this single queen will lay approximately 1,200 to 1,500 eggs per day. Ultimately, the hive will become congested and prepare to swarm. This is a frame of brood comb. In preparation for swarming, the worker bees will convert some of the eggs to queen cells, shown here at the bottom of the frame. About 7 to 10 days later, the hive will swarm. So what happens when a hive swarms? The queen leaves the hive with approximately 50% of the bees in the hive, or about 30,000 bees. They'll exit the hive rapidly, usually over the course of 2 to 5 minutes, and will usually land about 50 meters from the hive. Over the course of approximately 2 to 4 days, scout bees from this swarm will look for a new location to build a hive. This is a single swarm, and the bees were considerate enough not to land in a tree about 5 to 10 meters off the ground. It made rehiving them in that small hive off to the left very easy. And this is what it looks like to rehive a swarm. Because I was around when this hive swarmed, and because they landed in a tree only about 1 to 2 feet off the ground, I was able to easily rehive this swarm. The approximately 30,000 bees that remain in the original hive will attempt to raise a new queen from the queen cells left behind. This hive is called the daughter hive because the queen that is raised is the daughter of the queen that left in the swarm. This is a standard 10-frame Langstroth hive. It, or some variant of it, is used in most human beekeeping operations throughout the world. Each of the 3 sections is called a hive body or a super. There is a bottom board painted yellow in the above image, which is the primary entrance to the hive for the bees, and a telescoping lid painted white in the above image. One of the primary problems faced by beekeepers in the spring is that of swarm control. In a very real sense, a honeybee hive is a superorganism that reproduces every spring by swarming. It splits into 2, the daughter hive and the swarm. As a result, preventing that reproductive event is difficult, if not, and is not always possible. From the beekeeper's perspective, the bees that left in the swarm may or may not be able to be captured and rehived, especially if they initially land way up in a tree. Or if the beekeeper does not recognize the hive that has swarmed and they take off and find a place to build a new hive. Sorry. Or if the beekeeper does not recognize the hive is swarmed, and they take off and find a place to build a new hive. To a swarm of bees, a house is just a weird-looking tree and is therefore a good location to build a new hive. Your neighbors do not usually feel the same way. If this swarm is not able to be captured and rehived, a laying queen and half a hive of bees are gone. The daughter hive, which comprises the bees left behind, will begin the process of raising a new queen. If they are successful, this new hive will live. If not, it and the 30,000 bees left behind will die. As a result, a swarm event can result in a complete loss of a honeybee colony. Therefore, swarm prevention is key. However, the next best thing is immediate detection of a swarm event. And if it can be detected, the swarm can oftentimes be found and rehived. Further, the daughter hive, once identified, can be manipulated by the beekeeper to increase the odds of a successful requeening. My solution is, if I can't prevent the swarm, then I can monitor it for the swarm event. If I can identify which hive is swarmed and when, and if I know after the event, I have a good chance of capturing and rehiving the swarm and requeening the daughter hive. Obviously, I can't sit in front of the hive and watch it from sunup and sundown, but what I can do is attach a Raspberry Pi with a camera module to the hive and take a still image of the hive entrance every 30 seconds to monitor the egress of the bees from the hive. This is how I configured one of my hives for swarm monitoring. Sitting at the top of the hive is a weatherproof container which contains the battery and charge controller which power the Raspberry Pi, which is in the see-through container, attached to the hive just under the telescoping lid. The Pi camera is fixed in the enclosure pointing down at the bottom board, seen in purple, which is the primary hive entrance. So what am I expecting to see? This shows 3 images of the entrance to the hive over the course of 2 minutes, with images taken by the Raspberry Pi. During a swarm event, there will be a lot more bees emerging from that hive. My proposed project design is to use a Raspberry Pi to take an image of the entrance to the hive every 30 seconds. Using that image, I can count the number of bees at the hive's entrance, and from the counts over a time series, discern whether the hive is in the process of swarming. If it is, notify the beekeeper, who can then capture and rehive the swarm and make sure that the daughter hive is successful in raising a new queen. At this point, counting the bees becomes just a computer vision problem, and from that, determining if the hive is swarming is just a data analysis problem. I know, just, right? And the problem and the fun is in figuring out how to do just that. The first problem that needs to be solved is one of power and communication. Unfortunately, you don't find too many apiaries with power or internet connectivity. My apiary is no exception. Bees don't need electrical power or internet access. This project does. Electricity is needed for everything, from powering the Raspberry Pi and camera to setting up communications. The obvious solution is solar power. Everything is a logistical nightmare when you mix bees with electricity. In order to get the photovoltaic cables from the solar panel to the hive, I needed to bury the cables in PVC pipe. And the reason I had to bury it rather than just run cable across the ground is because apparently the indigenous wildlife out in my apiary seemed to have a taste for PV cables. Even with the cables being buried, they still seem to find a place and want to gnaw on the exposed section between the PVC pipe and the electrical enclosure. I can't believe wires actually tasted good. I have not yet repaired these cables or put something into place to prevent its reoccurrence. In addition, setup of a solar power system requires a bit more than bringing the PV cables to the hive. The first necessary component is an MPPT, or maximum power point tracker charge controller, which is an electronic DC to DC converter that optimizes the match between the solar panels and the battery bank. It converts a higher voltage DC output from the solar panels down to the lower voltage needed to charge the batteries. It is connected to a battery bank of deep cycle marine batteries. The trick here is to appropriately size the solar panels and battery banks so that during a normal day of sunlight, the batteries will power the device and still have enough charge to power the device at night and on subsequent cloudy days. Next in line is the very important 3-amp fuse between the battery bank and the buck converter. This fuse will protect downstream equipment from overcurrent situations from the battery that can result in damage to the Raspberry Pi or can easily result in a fire from current buildup in the battery. Most of the common batteries used in solar system setups provide 12-volt power. It's great for the battery, not so much for the Raspberry Pi, which runs on 5-volt power. In order to bring the current down to 5-volt, a 12-volt to 5-volt buck or step converter is needed. Finally, a USB cable can be connected from the buck converter to power that Raspberry Pi, but absolutely break out your voltmeter to measure the current being sent to the Raspberry Pi. Outside of 5 volts plus or minus 0.2 volts, and your Raspberry Pi becomes really flaky. Much beyond that, and you can easily fry it. This is a picture of those pieces of the solar setup sitting outside of the weatherproof box on the top of my observation hive. We're looking at the back of the hive, and the Raspberry Pi is attached to the front of the hive. Note the lack of a fuse on the positive line going from the battery in the watertight container to the buck converter. That mistake cost me about 2 weeks worth of work and about $100. This is the Raspberry Pi with the attached ribbon cable to the V3 camera attached to the bottom of the weatherproof enclosure. I had to Dremel out a hole for the camera, so I guess that doesn't make it all that weatherproof, but it was at the bottom of the enclosure, so I was pretty confident that rain would not get in. The RPI is shown here with the 6-fab data modem hat, which is the $100 that went up in a burst of electronic smoke. Internet access out at the apiary was a bit more problematic. The apiary is about 2,000 feet away from my house, so wireless connectivity from a standard access point was not sufficient. I opted to use the Ubiquiti Lightbeam 5AC, which is a wireless bridge designed for long-range point-to-point communications. Getting approval from the Domicile Beautification Committee, also known as my wife, to mount the station point seen here on the left on our house was not trivial. After some serious negotiations, I was able to obtain approval. The access point seen here on the right is powered by a PoE with the electricity generated from these 2 solar panels connected to an Ubiquiti SunMax solar point charge controller. The charge controller not only regulates the battery charge, but provides 24-volt DC power and 4 PoE ports. The black and yellow tote houses the battery bank. Monitoring of the equipment is crucial. Any and all components can and will fail. The batteries will run out of a charge, the charge controller will fail and stop providing power from the solar panel to the batteries, and the RPI will get fried because you forgot to put a fuse in line. If you spend time setting it up, spend a little more putting in some method of monitoring it. This is the web interface for the SunMax Solar Point Charge Controller. The uptime for this, when I took the picture, was 185 days. Sometime over the winter, there were way too many cloudy days and the batteries ran out of power. One of those PoE ports is connected to the Ubiquiti AC mesh access point, which provides the wireless internet access out at my apiary for the Raspberry Pi. Luckily for me, I had all this Ubiquiti equipment lying around before I started this project. Unluckily for me, it had been sitting around for quite some time and had since been discontinued, so no support, but everything worked. Now we get into the fun part, the Python programming. But first, let's look at the process pipeline. We're taking an image every 30 seconds with a Raspberry Pi V4 of our hive interests. Using computer vision and data analysis to determine if a swarm is occurring, and if so, notify the beekeeper via SMS notification. Using Amazon Web Services simple notification service. I decided to go with SMS notification rather than email because it's more immediate, and I'm using AWS SNS because email to SMS with the common couriers is getting a bit problematic of late. Right now, taking the images was done with an RPI version 4, while the rest of the project was done on an Intel i5 laptop or a MacBook M4, and the model training was done on an Intel i9 workstation with an NVIDIA RTX GeForce 4080 Super GPU. Except for the model training, my ultimate goal is to keep as much of the computer vision and data analysis process on the RPI as possible, but I'm not there yet. However, all stages were planned, and the assumption is that at some point they would be done on the RPI. The code to capture an image using a Raspberry Pi is not all that interesting. In fact, you might look at it and mistake it for a shell script. Version 3 of the Raspberry Pi camera uses the PyCamera 2 library. I just use the default parameters, which takes a picture in 640 by 480 resolution. This is fortuitous since PyTorch training prefers images at 640 by 480. In essence, the configuration parameters are set with the function create preview configuration, and then the image is taken with the start preview function. The next option that we need to look at is storage. Honeybees will only swarm during daylight hours and almost exclusively between 10 a.m. and 2 p.m. I decided to confine my monitoring between 8 a.m. and 5 p.m. Taking an image every 30 seconds means I'll be taking about 1,080 images per day. I configured the PyCamera 2 module to obtain a 640 by 480 image, which results in an image about 100 kilobytes in size. This means that I'm collecting about 100 megabytes of data per day, or about 3 gigabytes per month. Bees will almost exclusively swarm between the months of May and September, which means I'll have about 15 gigabytes of photos per swarm season. This easily fits on a micro SD card used by the Raspberry Pi, so off-site storage is not technically necessary. However, I needed off-site storage to easily be able to pick the files up for PyTorch model training. I also needed to submit the request for the AI analysis to count the bees in an image by submitting the URL of the image. AWS's S3 bucket provided both. So, to modify the process pipeline a little bit, we have an updated pipeline where We're taking an image and uploading it to an AWS S3 bucket, and they're all done on the Raspberry Pi v4. Interaction within AWS S3 bucket is very straightforward. The standard AWS library Botto3 is loaded. A session object is instantiated with keyword arguments. The client session is opened, and the files are uploaded to the given bucket. Nothing major. The next option that we need to look at is image pre-processing with OpenCV. Usually what we do is we have to normalize the image to the same resolution area on multiple images, but we don't have to do that in this case because they're all at 640 by 480. In addition to pre-processing with OpenCV, while not absolutely necessary, I've found that I get better results when I submit the image for AI analysis or for use in model training when the bees look like distinct individual objects rather than a bee blob. There are less than 200 bees in this photo, but you can see in the original image how they start to overlap and begin to virtually coalesce. In a swarm event, this is going to get much worse. I tried 3 different OpenCV techniques for processing the images. Linear transformation, which applies the same changes to all pixels. It's a very quick, computationally fast, but does not always do a good job as the contrast-limited adaptive histogram equalization, say that 3 times fast, where the image is broken down into a green to red channel, a blue to yellow channel, and a lightness channel. The lightness channel is then modified to obtain optimal results. Adaptive is kind of a hybrid between the two. I believe I obtained the best results with CLAHE pre-processing. So we now have the next step in our process pipeline, which is pre-processing using CLAHE. I thought this code was much more interesting. I wish I could say I wrote it, but I stole it from OpenCV's documentation. After loading the OpenCV library, which I didn't show here, in essence, it converts the image from red, green, blue to a lightness, green to red, blue to yellow color space. Then it tweaks the lightness factor and then returns it to a red, green, blue image. In a similar vein, OpenCV's documentation had great examples that showed how to pre-process images using linear and adaptive algorithms, which is also what I used to generate the images that I showed previously. After pre-processing with CLAHE, I first submitted the images to Marvin. After pre-processing the images with CLAHE, I submitted the images to Marvin.AI. Unfortunately, the code to submit an image to Marvin.AI is depressingly simple. Once the relevant image is being served by HTTPS, which since the image is stored on S3, that's more than half the battle, the Marvin.AI library is imported, and then it's a matter of asking the AI to count bees. I think it was this code that made me decide to train my own model and use it to count bees. I've been told that I like to overcomplicate things. The possibility of running an implementation of a YOLO V8 model on a Raspberry Pi to detect and count bees in real-time camera imagery is just a side effect. The machine learning pipeline of this leads to the question of how to use a convolutional neural network to develop a training model to count bees, which is what this is. I like to think of it much like you would an LLM. An LLM is basically a next token prediction engine. There's more to it than that, but at its core, that's how it functions. With a CNN, the first thing you do is annotate an image by specifying which pixels are part of the object of interest. Once you train the model based on a large number of images, it too becomes the next token prediction engine, where the token is not a word, but rather a pixel or a group of pixels. I've been told that this is an overly simplistic explanation, but not completely incorrect. That was by another AI, so who knows? Maybe it was just trying to suck up to me, but I'm just going to go with it. As you can see in this pipeline, the first task is annotation. I use a segmentation mask type annotation with OpenCV's tool, CVAT, which stands for Computer Vision Annotation Tool. In essence, you draw a polygon around the object to distinguish which pixels are bees and which ones aren't. I then use the YOLO algorithm. YOLO stands for you only look once. PyTorch uses that algorithm to train the CNN. That's as far as I got because I discovered that drawing a polygon around approximately 200 bees in each image became really old after just a few images. Also, swarm season ended. So now we have a new pipeline that takes a bit more shape, where the actual counts of the bees in the images are done by either Marvin or, better yet, my YOLO model. The hard part was generating the annotation file. That's shown at the top in the 2 lines, one from the original image that both of them were taken. This data was taken from one of the original images that I took with the Raspberry Pi. Each line are the coordinates of a polygon. The 0 is the object ID. I was only interested in bees, so I only have one object ID. If I had put in something like flowers, that would have been an object ID of 1 or something like that. The next set of numbers are the XY coordinates of each vertex that describes a bee in the image. CVAT will then take this XML file and convert it to YAML, which will then mathematically describe each polygon. I then import the YOLO module, which creates a base model and then uses PyTorch to further expand upon the model, which was very simple. However, now we have bee counts from each image. They also need to be analyzed for the potential of a swarm. And the first problem that we come across is that of bearding. This is not a swarm event. It's the bee equivalent of hanging outside on the front porch because it's too hot inside the house. Bees will stay like this for most of the afternoon and not retreat back into the hive until dusk. However, if making decisions based on the sheer number of bees at the entrance, this might be mistaken for a swarm event. The projected bee counts would look something like that described in the green line. If we were to look at the bee counts, we might mistake the increase in bees between 24 and 44 time units as indicative of a swarm. But if we keep looking at the data, we see that the counts never go down, except between units 54 and 59. This is the reason I decided on using a moving average of the counts. In my case, I look at the average number of bees over the course of 10 minutes, move forward 2 minutes, and take the preceding 10-minute average, and then continue. In this manner, we get the red line, which has the benefit of smoothing out both high and low transient bee counts. An actual swarm event will look like this, where 30,000 bees will emerge from the hive and fly around. The bee counts will dramatically increase, but they will fall rapidly since the bees don't stay at the hive entrance. This is a projected swarming data, of which the bee counts will look like over time and the 10-minute moving average. Data analysis where the moving average actually increases and then decreases would be indicative of a swarm event. So now we have a completed process pipeline, which I hope you'll agree is not as complicated as it looks. In this case, we're analyzing the bee counts because using a Pandas rolling window analysis. Luckily for me, Pandas actually has a moving average function since it is so widely used in biological systems and financial markets. First, the moving average is calculated over a given window size. Then the z-score is calculated, which is how far the bee count differs from the standard deviation of the moving average. A positive number means an increase in the number of bees at the entrance. A negative number means that there is a decrease in the number of bees. Based on my simulations, swarm events would vary between a base of about 10 to about 30 for a major swarm. But those are just my projections. I don't know how accurate that is. And finally, the AWS simple notification service that gets activated once a swarm event is identified. It's rather anticlimactic. So, what are the results? Inconclusive. That particular hive never swarmed. It actually died from parasitic mite syndrome, but that's another story. I also ran out of swarm season. So when I get back home, I'll be setting up another observation hive. So in conclusion, I'd like to thank Bob Belderbos and Julian Sequeira for their help and support. Without them, this project would never have happened. And I'd like to thank you for attending, and I'm happy to answer any questions either here or afterward. Sure. I'm sorry, what was that? Yes, bees will only swarm during the day, only during daylight hours, only during daylight hours, and preferentially between 10 a.m. and 2 p.m. Yeah. Three. I tell you, CVAT is a wonderful tool. It really is. But you've got 200 bees in there, and you start drawing, polygons around each bee, and like I said, it gets old fast. So it's something that I'm going to do in my spare time when I need to fall asleep. Yeah. An online service does just that. I wouldn't have to do that. It's called RoboForm, and what it does is you can actually do that where it will actually, you can submit your things, and it will actually generate the data and train it, and ultimately you can export it into YOLO V8 format. And one of the things that it's claim to fame is that it will help you in terms of those annotations. I just wanted to overcomplicate things. Yeah? RoboForm, yeah. Yeah.
So this is really like a great tool, I think, to keep track of these, especially if you're doing numbers. Could this theoretically be modified to keep track of any other ingredients?
Wow, that's a good question. I hadn't thought of that. I know that from experience with my family, they do deer hunting, and so they have a lot of different hunting cameras out there. And so I think something could be done with that. But in general, you're suffering from the same problems that you are with an apiary, in that out in that sort of forest type environment, you don't have electricity, you don't have internet access, and that makes things really difficult. Yeah. Oh, I've heard of that. I've heard of that. They're actually doing something like that when they are using, I haven't done that, and I haven't actually experimented or looked at that, but I have seen where there are some people who, I think some of the researchers, some of the bigger entomology schools where they're actually doing that sort of thing, and they're trying to monitor it by the sounds that varroa mites make. Seems kind of interesting to me, but I don't know. One more question? Yes.
Okay, the mic is working great. So, did you consider any other computer vision models other than YOLO V8? Like, I actually specialize in small computer vision models, like YOLO E or PicoDet may actually run on the Raspberry Pi for you and actually do what you want.
No, and I'm going to tell you why. The AI that I talked to that I learned how to do this from told me no.
Got it.
So
I run in production on thousands of systems. I can help you.
But the thing is that would be good. And what I did was, I really do think that AI is a great tool. I think it can be overused and used improperly, definitely. But I think it can be a really good tool to learn different things. So I will be happy to take any, sorry about this, but I'll be happy to take any questions afterwards. Please.